series this year with a topic polynomial optimization. And our MoCaO lecturer is James Saunderson this year, and he already gave the first lecture yesterday, and today will be the second lecture about polynomial optimization. So over to you, James. The Zoom is yours.
Great, thank you very much, and thanks everybody for returning. If you returned, I'm not sure if we have anybody new today. If you are new today, we are going to start a little bit in the thick of things, but hopefully you'll be able to hang on and understand what's going on. All right, so let's get going. So let me start by, okay, so what have we seen so far? So kind of what happened yesterday. So we looked at this family of optimization problems we call polynomial optimization problems, where we're trying to optimize a multivariate polynomial with real coefficients subject to polynomial equality and inequality constraints. So it's a very, very general class of optimization problems, sort of difficult, but very expressive. Okay, so we can model lots of interesting things, continuous problems, discrete problems, and so on in this form. Okay, and then what we did is we kind of flipped things around and looked at another class of problems that we might now call conic optimization with respect to non-negative polynomials. Okay, so this is a class of problems where we have a linear objective function, linear constraints, and our decision variable is now a polynomial. Okay, and so our decision variable is a polynomial or multiple polynomials. And the interesting constraints in these problems are the requirement that these polynomials be non-negative, either globally non-negative or non-negative over some set. Okay, so this was kind of, and what we saw is that, you know, if we could solve these conic optimization problems with respect to non-negative polynomials, then we'd be able to solve polynomial optimization problems. So kind of the top right class is somehow at least as powerful as the top left class of problems. All right. But the problem is, okay, that we've just shifted the difficulty, and in particular, we've shifted the difficulty into this convex cone constraint, this cone of non-negative polynomials. Right. So what do we then do? Well, we looked for things that are easier than non-negativity that might still be kind of powerful and that might be tractable for computation. Right. And so what we saw is that there's this notion of a polynomial that's being a sum of squares. Right, so a polynomial, if it's a sum of squares, then it's definitely non-negative. So the sum of squares cone is somehow inside the non-negativity cone. Okay, and in general, the converse is not true. So you lose something by going to sum of squares. But what you gain is that you gain, in some sense, you gain computational tractability. Right, so what it turns out to be true is that you can describe the sum of squares or relate the sum of squares cone to or describe it in terms of the feasible region of a thing called a semi-definite program, okay, which is a generalization of linear programming. And what's nice is that, you know, for semi-definite programs, at least ones that are not too big in size, we have quite reliable algorithms in practice to solve these problems. Okay, so what's the conclusion of this kind of story as we have it so far? Basically, we've assembled a bunch of pieces, is that we know how to optimize over the sum of squares cone using semi-definite programming. And so in principle, we can kind of unwind this story and replace non-negativity with sums of squares, and then rewrite our conic optimization or approximate our conic optimization problems with respect to non-negative polynomials as semi-definite programs. Okay, so that's kind of, we really last time, that's where we kind of got to, except for one more thing. The other thing we did is we did one example of showing how to apply this technique to an unconstrained optimization problem last time. Okay, so what are we going to do today? We want to go from this kind of thought bubble / assortment of ideas that sort of seem like they make sense to actually see how we can turn these into a kind of general and quite systematic tool to tackle polynomial optimization and decision problems. All right, we'll start with the unconstrained case. And what we'll see is that, you know, the vanilla sum of squares, you know, gives us some bounds on the optimal value of unconstrained polynomial optimization problems. And we'll see a technique to improve those bounds using what we call multipliers. Okay. Then we're going to go to look at the constrained case. So how do we kind of extend the ideas we've got to deal with constrained polynomial optimization, or if you like, to deal with describing non-negative polynomials or polynomials that are non-negative over some set. Okay. And then kind of once we've kind of developed sort of our tools and seen kind of get the idea of how they should work in this more general setting, what we're going to do in the last part of the talk is see how this fits into kind of a bigger story of certifying the infeasibility, or if you like, the emptiness of sets defined by polynomials. And we'll see that there's a really beautiful and systematic results about how you can do this, and that really what's going on in the tools that we're kind of developing in a somewhat ad hoc way throughout these lectures is that they're really they're really justified, if you like, by this theory of certifying infeasibility. All right, so that's kind of going to be the plan for today. But before we get too far, I wanted to just make this, like, at least once in these talks, make this kind of concrete, right? In the sense that I say, oh, once you can write this in terms of the sum of squares cone, then kind of you can go and solve this with a semi-definite program and blah, blah, blah. And this, I know when people tell me this in talks, I'm always like, yeah, but how do I actually do it? I just want to show you, like, from this very simple example that we did last time, sort of exactly what, what's some code you could write in MATLAB, for example. There's many different packages and things you can use to do this. What's some code you can write in MATLAB to produce a lower bound on the minimum of this polynomial, okay? A global lower bound on the minimum of this polynomial. So there's a package called YALMIP, which is kind of like a parser, okay? It kind of does high-level manipulations for you. And then this will call a solver MoCaO that's well known, that includes a very good semi-definite programming solver. And like, if you combine these two, you can get these bounds by just doing the following. So you set up a few variables, they're semi-definite programming variables, they're scalars, x, y, z, and a variable for this lower bound parameter. You define the polynomial. You say that I want my polynomial minus this constant gamma to be a sum of squares. Okay, that was our way of, that will prove that it's non-negative. And I want to find the largest gamma. The minus sign is because minimization is the default. I want to find the largest gamma such that this constraint holds. Okay, and this last thing is just telling us that gamma is an optimization variable. All right, and you go and do this, and it will, and this will give you the value of gamma. I just want to, like, I don't know if I can do this. I'm going to try to do a new share of my MATLAB window and show you what this looks like. So again, I think I've got the same thing in here. Hopefully I haven't messed it up. Maybe yep. So if we run this code, what will happen? Okay. So I'll just show you what gets, the whole rubbish gets spat out. We get a number out that tells us that this Robinson polynomial is at least negative 0.1388 globally. In fact, we know it's at least 0, but this is what the vanilla version of this technique can give us. And all the stuff that comes out is kind of, there's two things. There's, I won't say too much about it, but I just want to give you a sense. There's some stuff that this YALMIP parser did. And what it does is it kind of, tries to figure out what you've done. It tries to do some sparsity related simplifications. It tries to find symmetry. So it does some clever stuff to try to simplify things that, we're not talking about at the moment. And then it passes the problem down to a solver. And the solver goes and solves it, sets up an SDP and solves it in 9 steps of basically 9 Newton steps. Pretty amazing SDP solvers for a problem like this, and solves to some pretty high accuracies, like 10 to the minus 8, 10 to the minus 9, 10 to the minus 10 type things. Okay, and then this spits out our answer. So I just want to make it clear that, like, somehow there's technology that makes this actually quite easy to do in practice. Once you've written down these abstract high-level optimization problems. Okay. So let's go back to here. All right, and go, sorry. And let's get going. Okay, so last time we saw how to do this, how to lower bound unconstrained polynomial optimization problems using just sum of squares. Okay, so now I want to discuss how we can, go beyond that and not just get, lower bounds that are maybe okay, maybe not okay, but kind of get us hierarchy of problems that give us improving lower bounds at the cost of more computation. Okay, so for example, we could look at this basic SOS relaxation for a different polynomial, another sort of tricky one, the Motzkin polynomial. So this is one of our examples of a non-negative polynomial that is not a sum of squares. Okay, because it's non-negative, okay, we know the exact minimum is at 0. Okay, you can verify this by putting that at least it achieves value 0 by putting all of the variables x and y equal to 1. Right? But it turns out that if you go and try to solve this sum of squares program, so you want to maximize gamma such that p minus gamma is a sum of squares, this problem turns out to be infeasible. Okay, so the best lower bound that sum of squares can give you is -infinity, which is kind of disappointing. Okay, this is meant to be a useful tool. Okay, sometimes it doesn't give you meaningful bounds. Okay, so that's disappointing, but I claim we haven't squeezed everything out of this idea yet that we could have squeezed out of this idea. And that's what's going to be the next theme, is how we can improve these lower bounds, still using sum of squares ideas. Okay, so what's the idea? Is that we're going to use a thing called multipliers. Before we go there, I just want to ask, okay, I've claimed a couple of times this is a non-negative polynomial. Let me now convince you in 2 different ways that this is a non-negative polynomial. Okay. So in the first way, it's going to be an aside, and then the second way is going to be the kind of the theme that we're going to press on in this talk. The aside is going to be really the starting point in some ways for Marika's talk on Friday. Okay, so the aside is, and the classical proof of why this is non-negative, this polynomial, is you can think about the AM-GM inequality. So think about this polynomial, after rescaling a little bit, as taking the arithmetic mean of these 3 terms, okay, minus the geometric mean of these 3 terms, right? And you can see that if you simplify this out, okay, what's happened here? I feel like oh no, that's correct, yep. So there's 4 terms, the arithmetic mean of these 3, and then the geometric mean is this term. And so we know by the AM-GM inequality that this should be a non-negative, all right? So that's one way to see if this is non-negative. Okay, and this is really the starting point for a whole other way to approach polynomial non-negativity. But right now, today, we're going to think about another way to convince ourselves this is a non-negative polynomial. So what we're going to do is we're going to take our polynomial p and multiply by some nice polynomial that's non-negative, okay? In fact, positive except at the origin, in this case. And it turns out that if you take p and you multiply by this other factor, you get some new polynomial, and that new polynomial is a sum of squares, okay? Even though p wasn't a sum of squares, once I multiply it by x squared plus y squared, turns out that I get a sum of squares, okay? And so I claim that this is also, we can think of as a certificate that p is non-negative, okay? Because if p wasn't non-negative, I couldn't get an identity like this, right? Because the right-hand side always evaluates to something non-negative. This quantity always evaluates to something non-negative. You might worry about what happens when this quantity is 0, but turns out this is not an issue because of continuity and so on. Okay, so another way to say this, and we're not going to say it so much this way in these talks, but people often do, is that you can think about that this Motzkin polynomial, it's not a sum of squares of polynomials, but it is a sum of squares of rational functions. So you can extract that also from this identity. Okay, so this is going to be the key idea, is that we can get more certificates of non-negativity by using this multipliers, by multiplying by something that's obviously non-negative and trying to show that the result is obviously non-negative. All right, so this is a great idea, you know. To what extent should this idea work? Well, you know, Hilbert, again, was already interested in this. He'd already thought about this at some point, and he asked the question, again, back in the 19th century, whether all non-negative polynomials are sums of squares of rational functions, okay? Or if you like, whether there's always a multiplier you can put out the front that's a sum of squares to make the result a sum of squares. And this was shown in the 1920s by Artin that indeed this is true, that if p is a non-negative polynomial, then you can find a sum of squares to multiply it by, so that the result is a sum of squares. Okay, so this tells us that, you know, if we allow ourselves multipliers, we should, in principle, of potentially a high degree, we should, in principle, be able to really solve these unconstrained polynomial optimization problems using this kind of sum of squares with multipliers idea. So that's kind of on the plus side. And on the downside, Is it okay? Yeah. So you should ask always the question, yeah, these exist, these QIs and SJs exist, but how big does the degree have to be? And it is known that there are bounds on the degrees that depend just on the number of variables and the degree of P, but they are really, really, really huge, like towers of exponentials, huge. The beautiful work, it's only fairly recent, the last 20 or 30 years, where people have figured out even some effective bounds on these things. But basically, in general, you can't hope to get any reasonable degree bounds. The other thing is that in general, if P is non-negative, you can't hope to choose your multipliers that are independent of P. So you might want to choose, you might think, oh, I just want to choose a standard multiplier, like x squared plus y squared. In general, this is not going to work. Okay, so that's the other thing you have to be kind of aware of. And we'll see how that comes up when we want to use this in practice very soon. Okay, so how do we use this? I'm going to say in practice, there's kind of two options, and we'll see one option is directly ignoring one of the points that I put on the previous slide. Okay, so again, I'm trying to minimize my polynomial over the whole of Rn, so unconstrained minimization. So one option to do this is to be like, I'm just going to choose my favorite multiplier. I'm going to take the sum of the squares of the variables to some power. That's my favorite multiplier. And instead of trying to find the biggest gamma such that P minus gamma is a sum of squares, I'm going to try to find the biggest gamma such that P minus gamma all multiplied by Q is a sum of squares. All right, so I could always have so this is potentially, if P minus gamma was a sum of squares, multiplying it by another sum of squares will still make it a sum of squares. So this will only improve things. And so that's a reasonable technique, and this will potentially improve your lower bounds. Okay. So that's kind of option one. What's nice about this option is that this constraint remains affine in the decision variable gamma. Okay, because Q is fixed. So I choose my degree, I choose Q, and I do this. Okay. So what's option two? Option two is more in the spirit of the theorem on the previous slide, in the spirit of Artin's result, but it has a catch. Okay. So what's option two is to say, I'm not going to fix a multiplier, I'm going to fix a degree, and then I'm going to search over multipliers. I'm just going to search over sum of squares multipliers Q. Okay, so I'm not going to just have a decision variable that's a single scalar gamma anymore. Now I'm going to be optimizing over this parameter Q. The catch is that if we go down and look at what would happen if I optimize over Q and gamma, this thing is no longer then an affine constraint in the decision variables Q and gamma because of the product Q times gamma here. All right, so that's kind of not great. What's the workaround? The workaround is that, well, gamma is just a single scalar, so I can just do binary search on gamma, right? So I could fix a gamma, fix a gamma naught as a candidate lower bound, and see if I can verify that lower bound by searching for a Q that's a sum of squares, so that this resulting thing is also a sum of squares. Remember, P is a constant. It's just a fixed polynomial in this setup. Now I've made gamma a constant. So this is, again, a sum of squares program that I could rewrite as a semi-definite program. Okay? And so, some of the time I'll find that this problem is feasible. Some of the time I'll find it infeasible. I can use that to bisect and, hone in on a value of the optimal, on a value, a good lower bound, right? So that's the other option. And this is really like what the theorem on the previous slide would say is that, option two, if you choose this degree large enough, you should be able to kind of get as close as you want to the optimal value with this strategy. Okay, so that's kind of how we can use multipliers to progress. Okay, so before, where I want to move to is the constraint setting, and I want to kind of have a little interlude that's somehow between, or you could view it as being between the unconstrained case and between the kind of general constrained case. And it's kind of interesting in its own right. And in some ways, some of the results and ideas are easier in this setting, even though I haven't emphasized it in these talks. Okay, so the interlude is to consider homogeneous problems, in particular, situations where the polynomial we are interested in bounding, is in fact a homogeneous polynomial. Okay, so just a reminder, what's a homogeneous polynomial? It's a polynomial where all the monomials appearing, for example, one way to say it, where all monomials have the same degree. Okay, so for example, here's an example. Here's the polynomial, the Motzkin polynomial from previous slides, but in its homogenized version, where we've got an extra variable that kind of, bumps up the degree to be correct in the monomials that used to have lower degree. Okay, so we've kind of homogenized it. And now for a homogeneous polynomial, what happens is that if you scale on the inside, the scaling comes out raised to some power. Okay, so kind of, in some ways, it's natural to think about a homogeneous polynomial. For instance, think about its values on the unit sphere. Okay, because otherwise, the values will scale up and down as you scale the point. So the values in the unit sphere make sense. The idea of being non-negative makes sense. The idea of being strictly positive, except at the origin, also makes sense. But some other notions of optimization don't make so much sense. All right, so the natural optimization problem in this case would be to try to bound the value or try to find the minimum or the maximum of such a polynomial over the unit sphere. Okay, so this is kind of the more natural problem in the homogeneous setting. And something slightly different happens here. So before, when we were trying to reformulate this as an optimization problem over non-negative polynomials, what did we do? We took our polynomial minus gamma and we asked for that to be non-negative. And that would have given us a lower bound on the optimal value. And we try to find the biggest lower bound on the optimal value. That's what we were doing yesterday. In the homogeneous setting, kind of the right thing to do is to take your polynomial minus gamma times the sum of the squares to the right power, okay? If you're interested in optimizing over the sphere, and ask for that thing to be non-negative, all right? So it's fairly easy to check. So certainly if this is non-negative, then gamma is a lower bound on the polynomial over the sphere, because if I plug in points on the sphere, this thing equals 1, okay? And that just gives me the value gamma. But it turns out this is actually an equivalent reformulation. So it goes in both directions, and it's using the scaling kind of niceness of homogeneous polynomials. That's why that works. Okay. So then if I restrict to homogeneous polynomials, how does the kind of sum of squares, multipliers, all this story, does it change or is it the same? How do things work? Okay. So quickly, one thing that changes a little bit, but actually doesn't really change at all, is the situations where non-negativity equals sums of squares. Okay, so if you start with a homogeneous polynomial in n variables of degree 2d, non-negativity and sum of squares are exactly the same, exactly when the degree is 2, so just as it was in the case of non-homogeneous polynomials, or when p has 2 variables, okay, or when p has 3 variables in degree 4. So the only difference in the homogeneous setting on this when is sum of squares equal to non-negativity is that the number of variables has bumped up by 1. And that's really because you can go from a non-negative polynomial to a non-negative homogeneous polynomial by adding this homogenizing variable. And you can go back again by setting that variable to 1. And this doesn't change non-negativity. And it also doesn't change being a sum of squares. Okay. And again, in all other cases, there are non-negative polynomials that are not sums of squares, and you can get them by homogenizing your favorite examples that were not homogeneous before. Okay, so this is kind of nothing really changes in passing between the inhomogeneous and the homogeneous case in terms of non-negativity versus sums of squares. But there is one nice thing I want to mention that is a little bit nicer in the homogeneous case. Okay, and so if P is a homogeneous polynomial that is strictly positive, okay, then you can choose, you can fix multipliers. So you can find a big enough degree d prime and use, say, the sum of the squares to the power d prime times your polynomial, and that will eventually, if you choose the degrees big enough, be a sum of squares. So there's two things that are different here. One is that we're assuming homogeneity, and the other is that we're assuming our original polynomial is strictly positive. And under these two assumptions, you get this kind of uniform multipliers or uniform denominators type result. Okay, which is in some sense what we were doing in option 1 before in our using multipliers, where we just fixed a multiplier, and didn't worry about it too much. Okay. Again, there are degree bounds on the multipliers you need to achieve this, and they depend on the minimum value of your polynomial over the sphere. Okay, so it really matters that you're strictly positive. And this is kind of a later result in a line of work that started earlier about forms that are non-negative on the authored. Okay, it's not crucial you use this multiplier. Using any other positive definite multiplier is fine. Okay. So let's just use this homogeneous technology we've got just to look at one example, right? Before we move on to more complicated constraints. Okay, so I want to go back to the maximum clique problem that we talked about yesterday. So what's the problem? We've got a graph with vertices and edges. I want to find a subset of the vertices of largest cardinality so that subset is a clique in the graph. Okay, so it's a completely connected subgraph. Okay. And one of the formulations we saw for this last time is that we can maximize a homogeneous quartic. Okay, so every term here, there's a term for every edge in the graph. Every term has degree 4. Okay, we can maximize this over the sphere and get a number that, from which we can easily deduce the clique number of the graph. Okay, so we've seen that we can equivalently write this as minimizing gamma. So now I'm exchanging max and min because we're maximizing over the sphere, just to confuse everybody. So we're minimizing gamma such that gamma times sort of the sum of the squares squared, okay, minus this form is non-negative. Okay, so that is an exact reformulation of the problem. So I'm trying to minimize an upper bound on this polynomial, so that if I plug in points on the sphere, it will certify that my polynomial has value at most gamma. All right, and then there's the natural relaxations you get from, say, Resnick's result. Okay, would be to take multipliers here. So I'm going to choose a degree d. I'm going to multiply by the sum of the squares to the power d. Okay, and I could choose d equals 0, and I'm going to ask for this whole thing to be not just non-negative, but a sum of squares. Okay, and of course, as I increase d, I'm increasing the size of this, or the parameters in this sum of squares cone, and it gets harder and harder to solve this problem. And so just to give you an example of actually a graph that's fairly somewhat difficult for this hierarchy is this icosahedral graph. So this is the kind of skeleton of the icosahedron. It's a beautiful graph. The largest clique is 3 in this case. And this hierarchy is exact when you choose d equals 2. But if you choose d equals 1 or d equals 0, okay, the bound on the clique number that this gives you is, it gives you a bound, but it's not exactly the clique number. Okay, so already relatively small graph. This, starts to not work straight out of the box already. Okay. All right. So let's now move on to constrained polynomial optimization. Okay, so how can we deal with constraints in a similar spirit? Okay, so the spirit of what we've been doing has been trying to replace polynomial non-negativity with a collection of polynomials that are obviously non-negative, either because they're sum of squares or because of multipliers that retain being obviously non-negative. Okay, so how do we do this for constraints? And let's start with equality constraints. So how could we describe a bunch of polynomials that are obviously non-negative on this set? Right? So, well, the basic idea is to take polynomials that have the form, or one basic idea, have the form a sum of squares, and then plus something that's obviously 0 on the set. Okay? So if I take something that's, a sum of squares, this piece is obviously non-negative, and then I claim that an expression of this form will always be 0 if I plug in points from S. So why is that? Because on S, all of the F's vanish. And so because there's a factor of F in each of these terms, whenever I plug in a point in S, this second term is going to be 0. The first term is going to be non-negative because it's a sum of squares. And so overall, I'm going to parameterize a bunch of polynomials that are non-negative on the set S, but may not be non-negative outside the set S, right? We don't really know what happens outside the set S. Okay. So this is some description of a family of polynomials that are obviously non-negative on S. Okay. One interesting thing, new thing that happens that doesn't happen in the unconstrained case is that I could it's not clear what the degrees of the object are in this expression, right? So for example, I could potentially, this polynomial here, I might be interested in polynomials of degree 4, but I might choose sums of squares of degree 10, okay, because I can cancel out some of the high degree stuff in Q with the multipliers and these F's here, all right? So there's potential cancellation between the two terms here that allows you to use high degree Q and lambdas even to certify the non-negativity of a low degree P over S. Okay, so that's something a little bit interesting that goes on here. Okay, so how do we use this computationally? Again, notice that the variables here that we're searching over to find such a certificate are a Q that's a sum of squares and lambdas that are just polynomials. Okay, and this expression is linear in those variables, so that's nice. If we want to make this something we can do computationally, we need to bound the degrees. Okay, once we bound the degrees, the fact that Q is a sum of squares, we can express with semi-definite programming, and these ones in bounded degrees are just kind of parameterize a subspace of polynomials. Okay. Right, so let's look at an example of using this. So this is back to an example, a toy problem I put up on the slides yesterday. So imagine again, we've got a non-singular matrix and we want to know how much we can perturb the diagonal and remain non-singular. Okay. Right, so we decided that we could write this as a polynomial optimization problem of minimizing the 2 norm, for example, of the diagonal vector, subject to the sort of constraint of being singular. And we're really trying to, if you like, bound the distance from the origin from this bad set of singular perturbations. Okay, so using the ideas on the previous slide, how can we get a lower bound on the optimal value here? Well, we're going to maximize a gamma, which is our lower bound, subject to the polynomial we want to be non-negative over the set. Okay, so we want our polynomial x norm squared minus gamma to be non-negative over the set. So what are we going to do? We're going to optimize over a sum of squares Q. Okay, so Q is going to be a sum of squares of some degree in 3 variables. I'm going to have a lambda that's just any old polynomial, doesn't have to be positive or anything. It's going to be of degree 2d minus 3. Okay, and then I've got my original polynomial that describes the one constraint we have here. So why does it have degree 2d minus 3? Because determinant of a 3 by 3 matrix will have degree 3. And so for this, so for the degree of Q being 2d, for it to have any chance of being cancelled out by this other term, we need lambda to have sort of enough degree. Okay, so lambda has to be at least this degree. Okay, and so if you go and do this computation, I mean, again, we can write up a little bit of code in YALMIP and run it. What do you find is that if you choose Q to have degree 4, okay, the bound you get is 0. So this is a very uninspiring bound. I mean, we don't have to do any work to tell you that the minimum is at least 0. So that's kind of, okay, quite disappointing. I was disappointed when I computed that. Okay, but then if you increase the degree of Q to 6 and you search over Q of degree 6, then you get a bound that's at least positive. So there's some perturbation you can do and remain non-singular. Okay, and then it turns out if you go up to degree 8, the bound suddenly gets a lot better. And degree 10, I believe for other reasons that this is actually the correct value. This is actually the optimal value. Okay, so it's kind of interesting that you can get a good bound, but even in this fairly simple problem, you need to use a little bit of extra degree to get there over the sort of basic degrees in the problem. Okay, so hopefully that shows you a little bit how you can apply that general technique to a concrete problem. Right? Okay, so as equality constraints, how do I deal with, or how could we deal with inequality constraints? Okay, so again, what's the question is how do we write polynomials that are obviously non-negative on a set S defined by inequality constraints? Okay, and I should point out that, okay, inequality constraints do subsume equality constraints if you only want to worry about one thing. You can think about that. Okay, so what would be the first idea? Well, I want to describe non-negative polynomials. The polynomials non-negative on the set. So in the spirit of what we had before, I'm going to take something non-negative, okay, plus some non-negative things. So these are all going to be sums of squares, all these sigmas. I'm going to take a sum of squares, obviously non-negative, plus sums of squares times these g's, okay? So why is this give me things non-negative on S? Because on S, the g's are all non-negative. And so I'm getting, if I plug in an x in S, I'll get a non-negative number times the sum of squares, which is non-negative, plus the sum of squares. So I'll get something non-negative. Okay. And so that certainly gives us a collection of polynomials that are non-negative in our set S. Okay. And again, this is an expression that's involves sums of squares, which we know how to describe. And it involves some kind of, these g's are constants. Okay, so this is some kind of linear combination of sums of squares. Okay. That's all well and good, but you might say, okay, but like, this particular presentation of the inequalities, maybe there's nothing special about it. That I could potentially derive other non-negative functions, other functions that should be non-negative on here, and work with those instead. Okay, so what's the idea here? Is that, if G1 is non-negative and G2 is non-negative, then also G1 times G2 is non-negative. In fact, any product of the G's is non-negative. All right, so a kind of fancier collection of non-negative polynomials will be to take any subset of the inequalities, multiply them together. Okay, so basically writing redundant inequalities that don't change the set, and then take coefficients that are sums of squares, okay, in this sum. And notice also that I will include the empty set in here, so that I do get a sum of squares out the front. Okay, so I could take, this of course includes all the polynomials of this form, but it includes, it has more stuff in it potentially. Okay, so this is a potentially larger class of polynomials that are non-negative on this set. Okay, but the same, again, in the variable sigma I. Okay, this is again a linear combination of the sigma i's. So this is something that involves, sum of squares constraints on the sigmas and kind of linear combinations of them. So it's kind of still within our sum of squares programming that can be rewritten as a semi-definite program sort of language. Okay, so that's how we would do that. I don't have an example, but you can see how you could go about doing this. Of course, the challenge here is that to make this a semi-definite program, you need to bound the degrees of things that are involved. Okay, so bound the degrees of the sums of squares, but also typically, if you start to take products of too many of these constraints, all right, the degrees there are going to get really big. And in order to cancel out those degrees, you're going to need big degrees elsewhere. So somehow you typically bound the degrees of everything going on in this certificate to get a reasonable sized semi-definite program. Okay. So we've come to this in a somewhat ad hoc way, I would say. We've kind of, followed our nose and used sort of sensible constructions. But it's not so obvious, right, whether this first attempt or the second attempt is the right thing to do, whether we've captured enough stuff or we also need multipliers of some form to get, get enough non-negative polynomials on our set. So I think trying to understand how to do this systematically, or at least how to justify more systematically what's going on, is what leads me to this last part of the talk. Okay, so the last part of the talk is to really connect all this business about trying to describe non-negative polynomials on a set that we've connected to polynomial optimization to a kind of bigger picture of certifying infeasibility or emptiness of sets defined by polynomials. Okay, that's what I want to spend a bit of time on now. And so essentially, what's the basic premise is proving that, the minimum of a polynomial optimization problem is strictly bigger than some value gamma, 4 or whatever, is exactly equivalent to, this is I think an important point, proving that the following set defined by polynomials is actually empty. Okay, so if the minimum is bigger than gamma, then there's no way you can find a point X that is both in S and for which the value of this polynomial is less than or equal to gamma. Okay, so somehow we can think about optimization, but we can also think about proving infeasibility. It's kind of equivalent to proving lower bounds on optimization problems. And I want to point out something. If our game is going to be proving infeasibility of sets or emptiness of sets, I want to point out a kind of asymmetry that has been lurking since the first slide yesterday. Okay, it's fairly easy for me to convince you that a set is non-empty, right? All I have to do is give you a point, and we have to check that it satisfies each of the conditions that defines the set, right? So I don't tell you how to find the point, but if we've got a point, it's very convincing. It's much less obvious how to convince ourselves that a set is empty, right? And that's where the power of these, I mean, kind of everything we've been doing, but particularly these infeasibility certificates, it really does something non-trivial. And like it seems like it should be harder, and that's sort of a fundamental question, but it sort of seems reasonable that it might be harder to convince ourselves that a set is empty. Okay, so that's what we're going to be doing. And so far what we've done is we've talked about a bunch of different sufficient conditions for, positivity of polynomials on sets, but we now know we can think about that as also sufficient conditions for infeasibility. What we're going to see is that there is some powerful theorems that give essentially converse results, essentially give necessary conditions for infeasibility, or for sort of ways to prove infeasibility. Okay. So before we go into like the highfalutin stuff, let's talk about the case where all the polynomials have degree 1, because this is a super special case where, that is very different in nature to the rest of polynomial optimization. And this is, of course, the kind of linear programming world. All right. So suppose I've got a system of linear equations and linear inequalities. Okay. So a bunch of my variable is x. I've got, let's call them linear equations and linear inequalities. Okay. So there's a very old, classical result that gives us a theorem of the alternative, as it's often called, a characterization of when a system of linear equations and inequalities is infeasible. Okay. All right. So Farkas's lemma tells us that this system is infeasible if and only if some other system of linear equations and linear inequalities is feasible. Okay, and so that's kind of amazing. Okay, so it tells you that the original system is infeasible if and only if I can find a non-negative vector lambda and a regular old vector with no constraints mu that satisfies some linear equations. Okay, so geometrically, it turns, you can interpret these what's going on here as basically being a separating hyperplane that separates, the polyhedron defined by these inequalities and the subspace defined, or the affine space defined by these equations. Right, so that's one kind of interpretation. It's also relatively easy, or at least one direction of this is relatively easy to show by just saying that if you had a mu and a lambda that satisfied these equations, you can multiply on the left mu here and multiply on the left lambda here and recombine things, and you get an obvious contradiction. So you can't have both of these things holding at once. So the other thing to say is, for those who know linear programming, really what Farkas's lemma and really what's going on, this is a kind of restatement of linear programming strong duality. So the easy direction that says if you have these mu and lambda, then you can show the system is infeasible. That's really weak duality, the kind of easy direction of convex duality. And the hard direction is the only if direction, that you can always find a certificate of infeasibility of this form. Okay. Right, so that's kind of the warm-up. What we're going to see is that something somewhat similar is going to be true in this much greater generality for sets defined by polynomial equations and inequalities. So what's this result, or at least the way in which I want to phrase it? It's often called Stengel's positive Stellensatz, and it again gives us an if and only if statement for infeasibility of a polynomial system. Okay, so I've got a bunch of polynomial equations and polynomial inequalities, right? And what it says is that this is infeasible in Rn, so there's no vector in Rn that satisfies all these things simultaneously, if and only if there's a certificate of some form. And what we're going to see is that, so if and only if what? There exist some polynomials, okay, lambda I, a bunch of sums of squares, one for every subset of these inequalities, okay? So that if you take the sum of the lambda i's times the f's that define the equations, plus the sum of the sigma i's, the sum of squares, times appropriate products of the inequalities, you get -1, okay? So let's at least convince ourselves that one of the directions of this theorem we can understand, right? So one direction says, if I can find lambdas and sigmas, that satisfy this equation at the bottom, then for sure this system is infeasible. So why would that be? Well, if the system was feasible, I could plug in a feasible point x. Okay, this thing would vanish. This thing would be non-negative, but a non-negative polynomial cannot equal to -1, right? Because that's definitely not non-negative. Okay, so clearly, if I can find the lambdas and the sigmas satisfying this identity, then the system is infeasible. Of course, the amazing thing about this result is that the converse is true, is that, an expression of, whenever you're infeasible, you can certify that with an expression of this form. Okay, that's pretty amazing. Okay, and this form should look very familiar from some of the things we were talking about before, right? So what I want to do now is, I should say this. So, of course, if we, I've said nothing about the degrees of these polynomials and the degrees of these sum of squares expressions, all right? So if I want to actually use this for computation, again, if I bound the degrees of all those things, okay, then this is no longer if and only if. Of course, once I've bounded the degrees, if they're not big enough, then I'll only get one direction. But I can then search for a proof of infeasibility by solving a sum of squares program, which we know how to compile into a semi-definite program or a semi-definite feasibility problem. Okay, so we're going to see an example of that next. Okay, this is an example taken from a very nice book that has been helping me prepare these lectures. So semi-definite optimization and convex algebraic geometry. It's a collection of book chapters, but in particular, chapters 2 and 3 give you a really nice outline of this topic. So this example is taken from there. All right, so we're given an equation, so that's the circle, and then a couple of inequality constraints. Okay, and so how would you apply this technology to show this is infeasible? So why is it infeasible? Because there's nothing that's in the intersection of the two regions down here and in the circle. Okay, so this should be infeasible. Okay, we can do this without thinking at all. We just need to get our computer out. And what we're going to do with our computer is we're going to choose a degree bound. And it turns out if you choose degree bound of 4, that's enough. We're going to look for a lambda that is a polynomial of degree 4, 4 sums of squares that are quartics and 2 variables. And we're going to try to verify to find these so that this expression, which is again a linear or an affine constraint in the 5 decision variables, lambda, sigma 0, sigma 1, sigma 2, sigma 1, 2. So that equals -1. Okay, so this is a semi-definite programming feasibility problem. And if one goes and solves this, so I didn't go and solve this one, but if you go and solve this, it turns out that if you choose lambda 1 this way, sigma 1 constant, sigma 2 constant, sigma 1, 2 actually equal to 0, so you don't need this product term. And you choose sigma 0 to be this thing, which you can convince yourself is a sum of squares, okay, because this matrix in the middle is positive semi-definite, and these are just vectors of monomials, okay? And you could check that this identity holds, right? And so that is a completely, if I emailed you this data, you could check the identity, and then you would know for sure that this system of inequalities, this equations and inequalities is infeasible, right? So it serves as a really genuine certificate that we can write down concisely that proves infeasibility. Okay. So we've talked about infeasibility for the last few slides. I want to just now connect back to positivity over sets, correct? Because that's really where we started, and that was our original motivation coming from polynomial optimization. All right, so again, we said, remember from earlier that a polynomial being positive on a set is the same as the set consisting of membership in my set S together with the polynomial being non-positive is infeasible. All right, and notice we've got a negative sign here. Be careful. And my set's going to be the same one we've been using, polynomial equations and inequalities. So what does the positive Stellan tell us? It tells us that we could certify that P is positive on S by finding polynomials lambda I, and 2 collections of sums of squares, all right? And I'm writing it this way because, okay, I want to think about, as before, -1 equals some combination of the FIs with the lambdas. And then for the inequality constraints, I want to separate out this inequality constraint coming from the objective function from these inequality constraints coming from the set. Okay, so I'm going to take all the subsets that involve P, and that's where my sigmas are the multipliers for, and then all the subsets that don't involve P. Okay, and that's these ones, subsets of constraints that don't involve P. Right, and the only other thing to note is that in this case, you have a minus sign because of the sign up here. All right. Okay, so this is what the positive Stellensatz would tell you, that you can certify positivity, okay, by searching over proofs of positivity over S of this form. So this looks a lot like what we were doing before. Okay, we got all the products of the constraints with multipliers. We've got this linear combination of the Fs or polynomial combination of the Fs. The only other thing to notice here is that this also does ask us to use multipliers in front of our polynomial P. Okay, just as we did in the unconstrained case, kind of that appears here as well. Okay, and again, if we bound the degrees of everything, we're going to get an inner approximation of polynomials that are positive on the set that we can describe this all using semi-definite programming. Okay, so this is what we get kind of straight out of the positive Stellensatz. Okay, it turns out that, you know, under additional assumptions, you can get some simpler certificates. And I just want to briefly, vaguely mention these so you're aware. Okay, and I'm just going to say this in the case of inequality constraints. Okay, they're the kind of crucial bit here. Okay, so there's a version due to Schmudgen that says if your constraint set is compact, so things that life is a bit better if your constraint set is compact. Okay, so if your constraint set is compact, then you don't need the multipliers. All right, so on the previous slide, okay, I'm on the wrong page. On the previous slide, you don't need this red stuff here, but you still need all these products of the constraints in general, okay, to really certify positivity. Okay. And then another kind of assumption, and this is a result due to Puttinar, says that if S is Archimedean, and I'm not going to say what Archimedean is, but it's really like an algebraic certificate of being compact, if you like, not just topologically being compact, but really having algebraic proof of compactness. Then we can certify positivity of P on our set without using multipliers and without even using the products of the constraints. So really going back to the very basic sort of simplest version that we started with. Of course, it's unclear, you know, there's no degree bounds in any of these statements, or no, I mean, the vanilla statements don't have degree bounds in general. And so it's sort of completely unclear whether it's better to use the fancier hierarchy with lower degree multipliers or the simpler hierarchy of the Puttinar or Schmudgen type with higher degree multipliers. It's kind of unclear how these things compare. So just to be aware that it's not so obvious that simpler is better in some sense. Okay. What is clear though is that under the appropriate assumptions, as you increase the degree, you're going to get a hierarchy of convex optimization problems that will converge to you know, the optimal value of your original polynomial optimization problem. Okay, so this is kind of if you like the conceptual justification for this approach. Although I really have to warn you that in practice, you know, it's all very well to talk about taking the degrees very large, but except in very, very low dimensional problems, it's hard in practice to solve these SDPs as you beyond typically the lowest degree that makes sense. You're really kind of often looking for, can I solve the lowest degree problem where I get an interesting bound? That's often where the practical sweet spot is. Not always, not for every problem, but in many cases, that's really what we can hope to do in practice at the moment. Okay, and so what's the reason for this is really that, remember that, you know, sum of squares in n variables of degree 2, this is described by a semi-definite program that has matrices of size n plus d choose d by n plus d choose d. And so these are pretty huge pretty quickly, especially if n is not tiny. And so even just storing these matrices, they're typically dense, rapidly becomes prohibitive, and it's really a challenge to solve these problems at any scale. Okay, doesn't mean we give up, but it means people are thinking a lot about, you know, ways around this scalability challenge. And sort of Georgina's talk on Thursday is going to be really focused on some approaches to try to circumvent some of these scalability issues with vanilla sum of squares ideas. Okay, so just to sort of summarize, what have we seen today? So today we've seen, basically we've built out our bunch of ideas into really a collection of coherent, systematic collection of tools that allows us to bound constrained and unconstrained polynomial optimization problems. Okay, in the interesting direction, in the direction that that you can't do by exhibiting feasible points. So what's the basic idea is that we basically write increasingly sophisticated expressions that are obviously non-negative on the constraint set. Okay, and so we replace the cone of polynomials that are non-negative on the constraint set with these approximations that are built out of sums of squares. Okay, and what's crucial is that these expressions are typically, linear expressions in variables that are either unconstrained polynomials or sums of squares. And so we can recompile these things into semi-definite programs and solve them with semi-definite programming solvers. Okay. So that was kind of on the practical side, we saw concretely what you do. And in practice, you typically choose the degree bounds to be as low as you can to try to get something interesting first and see how you go. And we also saw kind of a justification for, what may have seemed like an ad hoc approach is that really somehow the sort of certificates we came to for proving lower bounds in our optimization problems or proving positivity over a set are really justified by these kind of positive Stellensatz results that tell you, really give you, a characterization of enough sort of the, how should I say it? Gives you a kind of guaranteed way to certify infeasibility of sets defined by polynomial equations and inequalities. Okay, so to wrap up, what are we going to talk about next time? So today we didn't have so many examples. So next time I want to spend a bit of the time connecting back to some of the examples we saw in the first lecture and sort of seeing how this technology can be applied to them. And then in the second part of the talk tomorrow, I'm going to zoom out and go more high level and just try to give a tour of a smattering of sort of recent research directions that people are studying related to this topic, that now you understand the basics, you can sort of understand and appreciate potentially what these recent research results and directions are all about. All right, that's it from me for today. Thanks very much.
Yeah, thank you very much, James, for this wonderful second lecture. And yeah, now I open the floor. Are there maybe some questions, comments? You can just unmute yourself or write in the chat.
Yep, anything is good.
We have still 2 minutes left here.
Still processing.
Probably.
Okay, I'll ask a question. How big a problem can you solve with these techniques, James?
Yeah, so how big is a piece of string, Andrew? No, I mean, but let me try to give you some examples. So I think, well, so maybe I should just, I'm going to do this just so I can look in my other window at the size of some of these problems I was solving earlier. So I was just trying to solve the independent set, the maximum clique problem for the icosahedron. It's degree 4 relaxation. So the graph's got 12 vertices. I'm trying to solve a sum of squares program there that had degree 12, I think. So this is kind of getting on the tough side. And I think the semi-definite program that Mosek was solving, I'm just trying to find it here. Maybe I'll just quickly run it privately on my computer so I can get the numbers right to give you an idea. It had some symmetry and so on, so it simplified things a bit. But I think it's still like many hundred size STP to solve this, 12 variables, degree 8 or degree 10 or something. So it gives you a sense of these things really, blow up on you quickly. But that's not, so, and what's being exploited there, I mean, even solving many hundred size dense STP is pretty hard. Because if you think about the variable, even just writing down, like you're working with a, 300 by 300 variable, that's, that's like 100,000, variables already. So it's, I mean, just doing dense linear algebra on variables of size 100,000 is quite impressive. So even for that problem, what's going on under the hood is there's a bunch of symmetry and things that are being exploited to simplify things. I would say kind of on the extreme other end, so very sparse, very structured semi-definite programs. So for example, ones that come out of the max cut problem that in fact I'll probably talk about tomorrow. These we can solve much larger instances when the problem is sparse. But there's a whole kind of litany of tricks that are going on there to be able to solve potentially problems up to like 1 million variables, like or graphs of size 1 million. So that means that if you were to write the SDP, it would be a million by million matrix. Right, so we're not writing this down explicitly, so there's techniques to try to avoid in that problem actually explicitly writing down the decision variable, and it starts to get very interesting, but very, very challenging, even just from a storage point of view when you want to solve big problems. So, but that's a case of many variables, but keeping the degree low. So the degree there is saying around 2. So.
This might be a completely stupid question, but I mean, you know, yeah, if you're just after an approximation, can you mess around with the cone constraint you're dealing with? Can you kind of make it a product cone of maybe linear parts get put into a polyhedral cone and the quadratic parts put into a sum of squares, or I don't know, you know, and then just look for something much more special.
Yeah, so I mean, there is
tractable, you know.
There is a different sort of line of work to try to, you know, make things more scalable. There's a couple of different ones. One, okay, so the sum of squares things generally produce you with big SDP cones, but can you do alternative formulations that use many smaller cones? So 2 by 2, lots and lots of 2 by 2 cones, which are much easier. Yeah. And really that's going to be the heart of what Georgina will talk about on Thursday, is that kind of idea.
Oh, okay.
Which you might find very interesting. I think the other thing people have looked at is whether you can, you know, can you take the PSD cone or your sum of squares cone, and I mean, there's all kinds of approximations you could imagine. Just keep some collection of extreme rays and use that polyhedral cone instead, right? And so while that can work sometimes, in general, it's known that you can't, that even using lift and project methods, you can't approximate the PSD cone with a polynomial, with a polyhedral cone of any reasonable size that you'd want to work with if you want to kind of globally approximate it. So it has to be that your problem is only looking at a piece that's actually much easier to approximate. So it's kind of, there seems like fundamental difficulties in general, and I think that really the opportunities are when you look at a particular problem structure and squeeze as much as you can out of it. That's when there's opportunities to do better. Yeah.
Okay, thanks, James.
All right, any other questions? If not, I think we can thank you, James, again for this wonderful lecture. And then we are up again tomorrow for your 3rd lecture, same time, same Zoom. Excellent. And yeah, have a nice evening.
Depending on where you are.
Exactly, or
day.
Or day, exactly.
Excellent.
And hope to see you all.